So I'm Andrew Hung. I'm a urologist in Southern California. I'm the Associate Professor of Urology and Computational Biomedicine at the Department of Urology for Cedars-Sinai Medical Center. And I'm going to share with you my team's work using AI and surgical gestures to predict patient-reported outcomes. This is my disclosure. And I am sponsored by the National Cancer Institute in the United States with approximately $10 million of active funding at the moment. So my team has taken surgical videos and we have decoded it to the moment-to-moment movements that a surgeon makes to complete a task, similar to the genomic code in human DNA. What do I mean by that? If you take surgical video, you can actually break it apart to the individual movements that a surgeon decides to make. That was a cut, this is a retraction, this is a peel, and this is an energy cut. So these are the building blocks of surgery. And what we have done is we have applied it to a procedure that has been done for decades, the nerve spare step of the robotic-assisted radical prostatectomy. Now, the problem with this particular procedure is that from the day that the procedure is done to the day that we realize whether or not a patient will recover sexual function or not is approximately 1 year. Now, I can barely remember what I did 2 weeks ago. Forget about something that's going to happen a year later. So what we did was using the concept of surgical gestures. We have broken up the nerve spare step of the prostatectomy. So these are the nerves that need to be preserved in order to preserve sexual function. And we looked at these 22 rows representing 22 patients, all undergoing this operation. And these are the first 100 gestures, dissection gestures, that are being performed, as I just showed you in the last few slides. Now, what's common about these 22 patients is that while they had sexual function at the time of surgery, a year later, they do not recover that function. In contrast, these are 18 additional rows representing 18 different patients undergoing this operation. And these patients do recover function 1 year later. Now, with traditional statistical means, you could say that, okay, the patients that recover function, the surgeons used more peel push. This is one of those gestures. And in essence, they're using blunt dissection to carefully preserve these nerves. In addition, they're using less energy to peel those nerves off. And that makes sense. And that's, not groundbreaking. But how do you understand more of that? Now, well, we took 150 odd patients undergoing this nerve spare step of the prostatectomy. This came from 5 different hospitals across the United States. And we looked at these gesture sequences during the nerve spare. That's approximately 80,000 individual gestures that we identified. And we also looked at the clinical features about these patients, their age, their body mass index, their severity of prostate cancer. And we plugged it into 2 different things. One was a basic neural network, and the other was a transformer that brought together relationships, and specifically within these gesture sequences. And we sought to predict 1 year erectile function recovery. Now, in addition to this sequence, and we've now been publishing on this concept of gesture sequences now for about 2-3 years, most recently in the Nature Digital Medicine journal, but it's not the sequence alone that's worthwhile. You got to provide a little bit more context. If you think of these gestures as individual letters of the alphabet, what are small groups of 5 to 10 of these gestures? Do they have a particular meaning, or do they have a functional unit or a function to them, such as peeling the nerve off the prostate or expanding a posterior plane underneath the prostate? And then furthermore, where are these gestures occurring? Are they occurring on the sides and at the bases of the prostate where the nerves are concentrated? Are they on the posterior end? Are they on the anterior surface of the prostate? That ought to make a difference as well. So this is ongoing work, but if you took just the clinical features, the things about the patient alone, you have an AUC of 0.7. That's, again, our ability to predict whether or not these patients will recover function 1 year after surgery. If you add just the gesture sequences, again, this 200 to 400 individual gestures that collectively make one nerve spare step, we get the performance up to the mid-70s. If you add those two things together, you don't get much of a big bump or a boost in performance of this model to predict this function. But if you add context to these gestures, again, taking that long string of gestures and you add context about the anatomy, you add context of what these small groups of gestures collectively are doing, we've boosted that performance into the mid-80s. And further, if you add all the patient characteristics, basically everything we know about the patient and everything we know about what the surgeon did on the day of surgery, we can predict with a very good accuracy whether or not these patients will recover function 1 year after surgery. So imagine that for a procedure that we have done for decades, and we've never really known from a data-driven manner how these patients would recover function. Now we can. But predicting an outcome is not good enough. What I've shown you up to now is our state-of-the-art, that we are able to predict this outcome, but that outcome is destined to happen no matter what. What we really are after, what my team is really after, is we want to know why, because we want to change destiny. We want to change what is already going to happen. So this is one patient who does recover sexual function a year after surgery. And this is that patient's string of gestures that his surgeon chose to utilize to perform this task. Now, there are groups or clusters of gestures within this long string of 400 gestures that are protective of this outcome, that they will recover function. And conversely, for a patient, this is a different patient, who does not recover 1 year after surgery, there are things that his surgeon chose incorrectly that increase the odds that he would not recover function at 1 year. So this is our aspiration. These last two slides are more of an aspiration of what we hope to accomplish. So as a take-home, with 150-some patients, this is an ever-growing data set from 5 different hospitals around the country, and we want to utilize them to train and predict patient-reported outcomes. Now, surgical gestures, as I shared with you, is perhaps one of those ways. It's the building block of surgery, and this could really be applied to any procedure that one does across procedures, across specialties. With our current model, AI model, we can use these gestures to anticipate a patient-reported outcome with great accuracy, and we think that it can help us identify, most importantly, where surgeons can improve their practice to therefore improve the outcomes of their patients. Thank you very much.
So first of all, good morning. Good morning to everybody. Okay, while they are loading the PowerPoint file, so just let me start by thanking Mr. Vattikuti and the Vattikuti Foundation for the invitation to be here. I'm really honored for the privilege to talk about surgical simulation. Okay, I also want to thank Chris Simmons for talking to me about this symposium last year when I met him at the SAGES meeting in Houston. Okay, here it is. Thank you so much. So, as you may see from my title, I work in bioengineering field, so I don't hold a clinical background, so I'm not a doctor nor a surgeon. And I'm pleased anyhow to talk about surgical simulation. As you may know, about 50 years ago, they thought that a successful and skillful surgical operation depending for about 75% on decision-making and 25% on the technical skills. So these percentages have been changed over decades after the advent of laparoscopy and robotic surgery, and probably now the weight of technical skills is much higher than before. And there are different grades about what we mean with skilled operations following the Dreyfus and Dreyfus model, which was adopted even in surgical training, starting from the novice level up to the master. And in order to discriminate these different levels, we use statistics. In surgical training, we usually set a benchmark level corresponding to proficiency, and we compute it using the mean of expert surgeons. And then, if we want to compute the expert level, we simply use one standard deviation above proficient, and the master is equivalent to 2 standard deviations above the proficient. On the other side, the novice is 2 standard deviations below, and the beginner was standard deviation below the proficient. So in this way, we can calculate, we can compute the competency level. So let me point out what happened at the beginning of the millennium during the Clinical Congress of the American College of Surgeons, where they invited 220 expert laparoscopic surgeons executing one task, the cutting edge, using either a virtual simulator or a box trainer. And the results were surprising, because about 7% was not able to complete the task at any platform. And another group from 2 to 12% scored more than 20 standard deviations below the mean, which is much lower than what we can see from the novice level from the curve at the bottom. And you may also be aware of another key publication by Birkenmeier, published in 2013 at the New England Journal of Medicine, where he correlated the different skills level of surgeons with patient outcomes. At the end of the study, they showed that the best surgeon with the highest skills level had the higher patient outcomes, so shorter operation times and least number of complications. What we did was simply figuring out what happened. So in my experience as a trainer in teaching activities and as a researcher, we didn't know, as always, and as you know, the proficiency gain curves of individual as depicted in this figure. There are 3 different learning curves. As you can see, there is no linear relationship between the number of trials and the proficiency in terms of trials and also time to complete the training. And this is correlated strongly with individual skills, what we may call innate ability. And in surgical training, we are used to requiring learners to reach the benchmark not just once, but at least twice in a row to show consistency. And it's not rare in my experience to find individuals, as in the case of the red curve, needing many more trials, because sometimes they're able to reach the benchmark, but then they fail to confirm it. So in this case, training becomes much longer. And we thought, can we use AI to predict the proficiency gain curve? So it was natural for me to analyze the data we collected over the years at a virtual simulator for robotic surgery by Mimic Corporation, now part of the surgical science ecosystem. And we analyzed the data from 176 medical students training until proficiency on 5 different tasks. And then we designed different machine learning models. At the end, ensemble neural networks outperformed the other machine learning models we tested. And this method allows us to select a threshold to predict the learning curves. For instance, for the first task called Pegboard 2, we only needed 5 attempts to predict the training time with an accuracy of 87% and number of attempts with an accuracy of 84%. For the second exercise called Ringwalk 2, we only needed 3 attempts to predict the training time with 89% of accuracy and 83% for the number of attempts, and so on for the remaining exercises. So this study could not be very important. The method illustrated could not be applied to an elite, to the best performing individuals. We previously showed in some studies on surgical simulation that there is an elite of about 6% of gifted individuals. We call them high talented. And in our experience, they didn't know mentorship by tutors because they are able to proceed independently of them throughout their training. But this method is really useful for the remaining of the population, which is 94%, considering those with average skills around 80–82%, and the low tail of the group, which is the 12% of individuals who traditionally struggles even on simple exercises. For them, this method can anticipate their proficiency gain curves. And potential application of this method are to design personalized surgical training based on individual technical skills, to estimate in advance the costs in proficiency-based surgical training, and to save time in a hypothetical aptitude test for surgery at a virtual simulator for the selection of the next generation of surgeons. So thank you for the attention. My presentation was short simply because I was told to follow the 5-minute template, but anyhow, if you're interested, I'm here all day, also tomorrow, and we can talk a lot. So thank you again for being here and for your invitation.
That was a wonderful talk. Can I ask you a question as to, at the present time in the UK and in Australia, where I'm from, it takes 7 years training at the same. Everybody does the same, even though they're quicker and more competent and more proficient. How much do you think you could shorten surgical training time by use of these algorithms?
So, thank you so much. This is a great question. And at the moment, I don't know exactly, but in the future, I think that with some research projects, we can try to modulate the length of the curriculum, because I think that the curriculum, or in general, training in any subject, should be like a suit. It's not the price, it's not the fabric of the suit that matters. It's the fit. I think this is the way. And with technology like AI, we maybe try to foster a flexible way of the curriculum, and some trainees maybe will be able to complete their training in a shorter time than the 7 years in the UK or other countries. For instance, in Italy, training is usually 5 years at least, but then there's a fellowship, so the training is longer. And as Michelangelo Buonarroti said, I'm still learning, so okay, official training is 5 or 7 years, but training continues throughout your life. But I would like to give you an answer, I don't know when, but thank you again for the question.
So are there any questions from the floor? Yes.
Good morning. Morning, Andrew. Welcome to India. I've been following your work for the last few years, inspirational work. I have one question. The data that you are collecting is actually predicting the outcome by looking at the annotations and data. Do you think this data can be utilized to train or warn surgeons that these are some of the actions they should or should not do while doing surgery? Are you working on that? Because that will ultimately make a difference in making a good or a bad surgeon. Thank you.
So nice to see many good friends from over the years. So absolutely, that's our bottom line. It's not okay to just predict outcomes, because those are going to happen no matter what. So our aspiration is to individualize and personalize training so that, you know, we don't think that, especially for the nerve spare step of the prostatectomy, it's not a single action. You know, it's rare in surgery where, sure, you know, there are instances where you make one bad laceration of the aorta, you could have a significant and terrible catastrophic outcome. But in most of surgery, that's not the case. In most of surgery, you're going to have very subtle movements that collectively will allow for a good outcome to occur. Or conversely, you have many small actions that increase the odds that a good outcome won't happen, right? So, and it could be different for every surgeon in the actions that they take down to the gesture level that we described. And so yes, that's our aspiration and goal, is that we will be able to identify a number or constellation of actions that a surgeon has done correctly or incorrectly.
How well you're able to standardize these tasks, and then also ability to correlate to each task for the proficiency and overall productivity?
Yes, thank you. Thank you for this question. Well, what we showed was only what is called in silico data, so data at a simulation, in a simulation environment, not in the real clinical scenario, but it would be very, very interesting to replicate the same method at a different level, not maybe now in the clinical, in the future of course, but to move from the simulation setting at a virtual simulator to maybe at animal level to see what happens on inanimate models with a real robot, to see if there's a correlation from the virtual environment to an environment using the real devices like the robot, on inanimate models, maybe later on animal tissue, and eventually on real patient, but this is a long, long process. I think that probably over the years we could do, but we need many resources, because this kind of study has most research activity based on AI need generalization from the training center to different centers to prove that the algorithm really works. But I think this is a long journey, but will be very nice to do it. Thank you.
I think the organiser should be congratulated for such a visionary session. We are at a tipping point. I think one of the big problems, and I said this yesterday, is that we were given as surgeons magnificent engineering technology platforms in robotics, but with no insights into how they work. And then we're also asking our surgeons to change from a 100-year-old way of training surgery to train in an engineered platforms of high sophistication. So that I think what we're learning from this discussion over the last few days is that we need a new curriculum purpose-built for our trainees, such that they can be monitored with the algorithms we just heard, and they don't have a one-size-fits-all philosophy. So trainees who are very rapid adapters should be pushed to finish their training more quickly, because one of the problems we have is not enough surgeons. So I think the future will be shorter training, more fit-for-purpose training, and assessing candidates, assessing their progression to proficiency. Are there any more questions? Okay, I think we'll finish the session, and thank you very much to our speakers.